So far, all the definite integrals that we've looked at have two things in common. Both limits have been finite, so the a and b in our definite integrals have been finite, and the integrand has been, worst case scenario, it was like piecewise continuous. So maybe there was like a jump discontinuity in our piecewise functions. But now we're going to look at types of integrals where one or both of those properties are no longer true, right? And we refer to those as improper integrals. Now, you have to be careful because the word improper kind of shows up two places, right? So we know what it means for a rational function to be improper. Now we're going to talk about what it means for an integral to be improper, right? And just to kind of give you an idea of both of them, and we're only going to look at one of two in this particular video, but let's say, for instance, we have a function and yeah, so like here's our function, and we know, for instance, how to find the area of our function as x goes from a to x equals b, right? Right, so if we wanted to represent that shaded area, we would use a definite integral, and assuming this is the equation y equals f of x, then our area under the curve from x equals a to x equals b would be given something like this. And now we have so many different, types of integration techniques. So hopefully one of them will work. They don't always work, but many of them, especially in your intro um, calc courses, they're set up so that one of the techniques will work, and we can evaluate it. We find our we find our antiderivative, plug in the upper, plug in the lower, and then take a difference. Right? And that's what our fundamental theorem says. As long as we have a continuous function on a closed interval, then we can do this. But then here's the question. What happens? Right? What happens to this process if b goes to infinity? So what if there was a slider here, right? And you kept pulling your b further and further to the right so that the area now is no longer bounded here, so it no longer stops at that point, but instead your function goes on forever, and so does the region, right? So what if that happens, right? Does it mean that the area has to be infinite, right? If the interval of integration is infinite, right? And then not only that, but what if a goes to infinity? That could not infinity, but negative infinity. So what happens if, let's say, your lower limit goes to negative infinity? Yeah, so instead of stopping here, what if it never stops? Again, what if your function is nice and continuous and it looks like this, but now our region is no longer bounded, right? So when at least one of your limits, your a or b, right, goes off to either positive and or negative infinity, the interval is now infinite, and we say that we have an improper integral, right? So when this happens, the interval of integration is now infinite, right? And we say the integral is improper. So the integral is improper. So that's one way that it can be improper. All right? That's where one of your limits go off to either plus or minus infinity. Well, something else could happen. So again, the fundamental theorem says the function has to be continuous, or at the very least piecewise continuous. But what if that's not true? What if, for instance, let's say you have your A and B, but now, just as an example, what if B happens to be a vertical asymptote of your function? So your function starts off, but then your function becomes infinite. So that now your region goes like that, right? Right? So again, if your function, your f of x, so if f of x has a I'll remind you of this type of discontinuity. It's referred to as an infinite or essential discontinuity. So if f of x has an essential or infinite discontinuity, right, on the interval, it could be at the it could be at the upper limit, it could be at the lower limit, or it could be somewhere in between, right? So somewhere on the interval, right? Then again, the question is, what do we make of this area where the region is still unbounded, but now it's going up indefinitely, as opposed to going, to the right or to the left indefinitely. But either way, we have an improper integral, right? So this leads to another form of an improper integral. Right? So when you look at it, it's like to have an improper integral, something has to go off to infinity. Something has to tend in some way in an unbounded fashion. So it could be either be unbounded because the interval itself is unbounded, right? Having either no upper limit, no lower limit, or neither, right? Or it could be your function, right? Your f of x could be unbounded. And in both cases, the fundamental theorem doesn't directly apply anymore, because the fundamental theorem says you have to have a piecewise continuous function. Piecewise continuous functions can't have vertical asymptotes, right? On a closed interval. Well, if your interval is closed, then you can't have infinite limits like negative infinity or positive infinity. So as it stands, our fundamental theorem is not really helpful. But there's a way we can modify this. We can modify what's happening here in the blue or what's happening here in the red in such a way that it's almost like we can simulate either the limits getting very, very large or the function getting very, very large. And I use the word simulate because it's like we're going to pretend for a second that the integral is proper, right? And then use limits to determine what happens when either the function, when your x gets closer and closer to this point where the function has an infinite discontinuity, or as your limits get larger and larger in an unbounded way, either going to positive infinity or negative infinity. All right. So what we're going to focus on in this video is the first type, where the lower and or upper limits are infinite, right? And what we're going to do is write down the definition and then do a couple examples, right? And they even have a name. Integrals with infinite limits of integration, so that's for A or B, right? And or I should say, so are improper integrals of type 1. So we refer to them as type 1. Right? And there are three definitions we need to write down. So if f of x is continuous on the interval, forgot my x, or x is greater than or equal to a, right? So again, there's that infinite upper limit. Then how do we make sense of something like this where we have an infinity at our upper limit, right? Well, we're going to use a limit to evaluate this, right? So what we do is we first put a placeholder where the infinity is, and we use b because b is typically our is the symbol that we use for our upper limit. So we put a b there, and then we're going to evaluate this the way we normally do. We're going to find an antiderivative. We'll plug this placeholder in, and this lower limit, which is presumably going to be a number, right? And what we're going to get is actually an area function. We're going to get an area function that gives the area under this curve from x equals a, which is my fixed number, to my x equals b, which is our placeholder. And then we're going to ask ourselves, what happens to that as b gets very, very large, right? So we take the limit of this area function, right? So I'm going to, let's highlight this or just indicate that this is an area function over the interval a to b. So it's a two-step process. So step one, we're going to find this area function, and it's going to be something in terms of b. It's not going to be a number because the b here is going to represent this, a placeholder, and then we're going to say, after simplifying this, what happens to it as b gets very, very large, right? And then there's some terminology that we're going to refer to after we've stated all three definitions. The second one says, well, if f of x is continuous on the interval negative infinity and your x is greater than negative infinity but less than or equal to b, right? So now it's the lower limit that's infinite, and we're going to end up doing something very similar. We would write this down, but again we're going to think of it and we're going to evaluate it in this two-step process. I'm going to put a placeholder where my negative infinity is, and what letter do we use? Well, we're going to use A, right? And we're going to evaluate this. So it looks a lot like the first one, right? Because again, this is what our fundamental theorem can help us with. It can't really help us with infinite limits, but we have the concept of a limit from Calc 1. Particularly, we have a concept of a limit at infinity, where our variable, or in this case our placeholder, can either go to positive infinity, or in the case of the second definition, a goes to negative infinity. So again, we start with an area function, right? We're not going to get a number now because the lower limit here isn't going to be a number. We're going to create what we're going to call an area function and then see what happens to that area function, as in this case a goes to negative infinity. All right. Third one is just kind of a combination of the two. So what if the lower limit is negative infinity and the upper limit is positive infinity? But what if your function happens to be continuous on the entire real line? So if f of x is continuous on the entire real line, then how do we define an integral, a definite integral? Well, actually it's an improper integral going from negative infinity to positive infinity. Well, because the function is continuous on the entire real line, we can actually use the additive properties of definite integral. We could, for instance, go from negative infinity to any number c, any real number c, and then go from that real number c to positive infinity. So we're splitting it up, and we then apply our definitions from the first two cases, right? So this one looks like the number 2 definition, and this one looks like the number 1 definition, right? So I'm not going to restate it, but that's how we would handle when both upper and lower limits are infinite, right? So here is some terminology. In each case, if the limit that we are going to compute, so if the limit is finite, in other words, we get a number out of this, we say that the improper integral converges, right? And the limit is the value of that improper integral. So if the limit, when we compute our limit, if we get a number, we say that the integral converges and that the limit is the value of the improper integral. Right? And if the limit fails to exist, right? So if the limit fails to exist, and again, think back to your first course in calculus, we saw a lot of limits that didn't exist. So if the limit fails to exist, the improper integral diverges. All right, so diverges just means that, yeah, as we let our upper and or lower limits go to plus or minus infinity, then the area function doesn't approach a fixed number. It might oscillate, or it might go off to infinity or negative infinity itself. But in any of those cases, we would say that the improper integral diverges. If, however, our limit comes out to be a number, in other words, if it's finite, then we say the improper integral converges. All right? All right, let's do a couple examples here and see what this whole process looks like. All right, so let's say we have something like this, the integral from 1 to infinity, and here is our function, the natural log of x over x squared dx, right? And so we could actually kind of visualize what this means. Like this, the graph of this function, it's not that odd of a function, or meaning the graph doesn't look really strange. But at x equals 1, it's going to be 0 because the numerator is 0 and then you have a 1 in the denominator. So it starts up here and it increases, and then after a while it starts to decrease like this, right? But what we're saying now is we're not stopping this region at any particular point. So it goes on indefinitely, right? So it just goes on indefinitely. And the question is the area in blue, does it come out to be a number, or is it infinite? Is it infinite, right? Well, we're going to apply our definition, and step 1, we're going to compute the area function, right? So we're going to evaluate the integral from 1 to b. So again, what I'm going to do is, like, just for this moment, I am going to say there. I'm just going to stop it and say, let's find that area in green, right? In fact, but it won't be a number, it will be an expression, right? So whatever b is, my expression would give me that green area. And then we're going to say, what if I let b go to infinity, right? So that essentially is the two-step process, right? And that's what we look for when we're looking at a solution for an improper integral. Is there an appropriate area function being used? And then is there an appropriate limit being evaluated? And are we using our appropriate limit techniques from Calc 1, right? So let's see what that whole process looks like. Now, for this one, I'm going to write this as x to the negative 2 and then times the natural log of x dx. And this is our integration by parts. Good old Lie-8, right? So I am going to, so in Lie-8 starts with an L, so by default, right? I mean, once you have a log function, as long as there's not something like a substitution that you can use, this is our L type, and here's our power function, which is our algebraic type. So that's our A type. So we're going to let u be the natural log of x, and then dv will be x to the negative 2 dx. Right? Differentiate this, so du is 1 over x dx, and integrate this. So v is negative x to the negative 1, or I can just write that as negative 1 over x. So our area, our definite integral is, so applying our parts formula, it's our uv, so this term times this term. So we have negative 1 over x times the natural log of x, and then minus the integral of v du. So negative 1 over x times 1 over x dx. And then notice I can take out this negative sign. So I have my negative 1 over x times the natural log of x plus the integral, and then I end up getting x to the negative 2 again. And that happens a lot with integrals of this form. Now, as far as the limits are concerned, this needs to have the 1 and the b, this needs to have the 1 and the b, this has the 1 and the b, this has the 1 and the b, right? if you wanted to, you could do it just as an antiderivative and get the antiderivative at the end and then use your fundamental theorem. Right? So we have negative 1 over x, natural log of x from 1 to b. Integrating this gives me the same negative x to the negative 1 from 1 to b. Now, because the upper and lower limits here are the same, I can group these together and just do one evaluation. So I have negative 1 over x times the natural log of x minus 1 over x evaluated at 1 and at b. Right? So at the upper limit, again, it's not a number. We're just going to put this expression in. So it is negative 1 over b times the natural log of b minus 1 over b. So that's what I get when I put my placeholder in. And then at the lower limit, the natural log of 1 is 0, so I'll have minus 0, and then I will have 1 over 1, so minus 1. So here's our area function. So in fact, so this is a positive 1, so I'll put the positive 1 in front, and then I'll write this as minus the natural log of b over b, and then minus 1 over b, right? So this is our area function for this natural log of x over x squared from 1 to b, right? And by itself, it can't really tell us anything. So now we have to ask ourselves, and here's our step 2, what happens to the area function as b gets very, very large, as b goes to positive infinity? So step 2, evaluate the limit as b goes to infinity of this expression, right? Minus 1 over b. Right? Now, this is a good reminder of some of the limit properties and procedures from first semester calculus. So we have we can take the limit of the individual terms. So this is the limit as b approaches infinity of 1 minus the limit as b approaches infinity of the natural log of b over b, and then minus the limit as b approaches infinity of 1 over b. Now, the limit of a constant is that constant, so that's 1. This is one of those special limits where the numerator is a constant, but the denominator is getting very, very large. So it's that convention that 1 over infinity is 0. That's what this is. So I have minus 0 there. Unfortunately, the 1 in the middle is an indeterminate form, right? Because as b goes to infinity, in fact, let me just kind of highlight this. And no, I'm not using red because it's dangerous, but I guess maybe some of these limits might be dangerous. But this, the numerator goes to infinity, and so does the denominator. So this is an indeterminate form. And there are lots of ways you can handle indeterminate forms. But one of the most, I would say, effective and efficient ways to handle this is by using L'Hopital's rule, right? So we're going to use L'Hopital's rule to evaluate this limit in the middle. And remember what L'Hopital says. It says, so let me switch back to my white. So when I apply L'Hopital's, I like to put a little L over the equal sign just to say at this step I'm using L'Hopital's rule. And it says if you have a limit of the form either 0 over 0 or infinity over infinity, you can replace this limit with another limit that involves taking the derivative of the numerator and the derivative of the denominator separately. So this is still a limit, and it's the limit of, now take the derivative of the natural log of b, that's 1 over b. Take the derivative of b, that's 1. So now the middle one is no longer indeterminate. So let me keep writing the 1 minus, I'll stop writing the 0, and then what I have here is the limit as b goes to infinity of 1 over b. So the middle one actually converts into one similar or identical to the limit as b goes to infinity of 1 over b. So this also approaches 0, right? So these are equal, 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 so 1 minus 0. So what happens is this improper integral, right? So let's summarize this now. So therefore, the integral from 1 to infinity, the natural log of x over x squared dx, this converges to a value of 1. So that integral converges to a value of 1. And what that means is that area that I sketched, and I'll sketch it again. So here's our function. So the function that I'm drawing here is the, let me label it, y equals the natural log of x over x, going from 1 now to infinity, is the further I go to the right, so starting here, so let's say I start just accumulating area. So like each one is like a new upper limit. I just keep accumulating area and I never stop. Then that area approaches a value of 1. So the area under this curve from 1 to infinity, it approaches a value of 1. So that's where we say converge. It's like it's getting closer and closer to 1. And I can get it as close as I want. So like if I want the area under this curve to be 0.999999999, then there is a b, there's an upper limit I can use. It might be very, 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 very large, but there's one out there that would give me that area that's super, super close to 1. And if I want to get even closer to 1, then I just have to make my upper limit bigger and bigger and bigger. So if I continue that process indefinitely, right, then my area will get closer and closer to 1. Right? And that's the process. It's a two-step process, and it involves, again, two big calculations that we do in calculus. First, obviously, the antiderivative and finding these new area functions in terms of either a or b, and then the second big process is that of a limit, right? So I hope you found that interesting, and in the next video we're going to look at the other type and see what sort of limits we have to compute then. See you soon.